Okay, so we're going to review graphing rational functions. Basic idea is going to be to factor our rational function, identify any vertical asymptotes, any holes that occur from canceling factors, and then checking for a horizontal asymptote with our little guiding rules there, and then plotting points strategically to include the intercepts and complete the shape of the graph. So the first thing we want to do is get a rational function in factored form. Then we're looking for removable discontinuities. This happens when you have the same factor in the top and bottom. So in this function, x minus 3 over x minus 3 cancels. So remember, the denominator x can't be 3 because that would make the denominator 0 and division by 0 is undefined in our number system. So it does still not exist in the domain of this function. It's definitely not in the domain. But what's going to happen there, because that factor canceled out of both the numerator and the denominator, rather than having an asymptote, we're going to have just a hole in the graph. Okay, to find the y-coordinate of that hole, you plug in the x-coordinate that would make that factor 0 into the remaining function, because for the rest of the time, this is the function that we're using to graph, the x minus 5 over x plus 2. So we would say y equals, plugging in 3 for x, 3 minus 5 over 3 plus 2, and that's going to give me negative 2 over 5. Okay, so we have a hole at 3, negative 2/5. All right, now, so a vertical asymptote is a non-removable discontinuity. So that hole was a removable discontinuity. We canceled that factor or got rid of it. But a vertical asymptote is what's left that makes the denominator 0 when you can't get rid of it, okay? If it ever looks like you have both a hole and a vertical asymptote, the vertical asymptote trumps the hole. And remember that a vertical asymptote can never be crossed. So what are we looking at? If this function instead had two factors of x minus 3 in the denominator, so x minus 3 quantity squared, then that x minus 3 on top would cancel with one of the two on the bottom. So you're like, oh, well, that factor cancels. So you might be thinking whole, but we're still left with an x minus 3 in the denominator, which means we very much still have a vertical asymptote at x equals 3. And at x equals negative 2, because those are going to be the values that still make the denominator 0. Okay, a crossing point is where the graph crosses a horizontal or oblique asymptote. You set the horizontal or oblique asymptote equal to 0 and then solve for that value. Remember, it's vertical asymptotes that can never be crossed. Horizontal and oblique asymptotes, their function is to limit end behavior. So in the ends, the function will approach that asymptote, but in the middle of the graph, it may be crossed. Okay, so a rational function has at most one horizontal asymptote or oblique asymptote. They limit the end behavior of a rational function as x approaches infinity or negative infinity. To decide which one we're going to have, we're going to compare the degree of the numerator to the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote at y equals 0. We like to say if the degree is big or below, horizontal asymptote at y equals 0. In purple here, I have little rhymes that my students came up with to help us remember that, so I think they're super helpful, but I still use them. Okay, the next case that we're going to have, if the degree of the numerator is equal to the degree of the denominator, then we'll have a horizontal asymptote at y equals the ratio of the leading coefficients. So our rhyme is, if the degree is a tie, the fraction in front equals y. We're going to look at the ratio of the leading coefficients. That fraction out front will be our y value for our horizontal asymptote. Now, if the degree of the numerator is equal to 1 more than the degree of the denominator, so the degree of the numerator is bigger by 1, then we have an oblique asymptote. It's y equals the quotient without the remainder. So we're going to see an example of that where we do long division. The quotient, the answer we get without the remainder, will be the equation of our oblique asymptote. So what's our rhyme there in purple? If the degree on top is bigger by 1, oblique long division, and you're done. Okay, so if the degree on top is bigger by 1, oblique long division, and you're done. Okay, if the degree of the numerator is greater by more than 1, then there are no horizontal or oblique asymptotes, which just means that the end behavior is not limited in this way. Okay, so oblique, and again, there we have a nice pretty picture in green of that oblique asymptote that's limiting the end behavior. Okay, so if you were wondering why this works, just a quick little why. This may be helpful to some of you. If we think about the degree of the numerator being less than the degree of the denominator, for example, just a plain x, which would be our linear function here in blue, whereas x squared, the bigger below, the horizontal below would be bigger below, would be the red graph of our parabola, we can see how much more quickly the values in the denominator are getting big. So if you think about fractions, if your numerator is smaller than your denominator, it's going to be a small number or decimal part of a whole unit. And so the bigger that denominator gets, and we know exponential functions increase so much faster, that denominator is getting huge and the numerator is getting bigger, but not nearly at the speed that the denominator is getting bigger. And that decimal just gets smaller and smaller. And so it will approach y equals 0 as we go to infinity and negative infinity. So that's kind of why that works. Okay. Similarly, if the degree is a tie, then the leading term, which is the one that's getting bigger fastest, okay, those other terms become insignificant as we approach infinity and negative infinity at really huge and really small numbers. Those other terms become insignificant. So the leading term becomes the driver of what's happening. And because those powers are the same in that leading term, it's really just the ratio of the leading coefficients that'll tell us how they compare. So in this one, we would have a horizontal asymptote at y equals 3/4. Okay. And again, this is just explaining the logic if we're wanting to understand that a little bit better. Okay, so let's try using this. It says to determine the type of asymptotes for each. If horizontal, give the equation of the asymptote. So here I see the degree is a tie, so the fraction in front equals y. So this is y equals 3/4, and that's a horizontal asymptote. Okay, here the degree is bigger below. 4 is bigger than 3, so bigger below, so horizontal asymptote at y equals 0. Okay, here bigger below, because 2 is smaller than 5, so bigger below, so horizontal asymptote at y equals 0. Okay, here the degree is a tie, so the fraction in front equals y. That 2/1, so that's going to be y equals 2. So it's going to be a horizontal asymptote at y equals 2. Okay, so a little practice with those. Okay, so if we take a look at this function, we need to get it in factored form to see what our vertical asymptotes are and if we have any holes in the graph. So let's just start factoring this function. Okay, so 2x squared breaks down to 2x and x. We want factors of -6 that add to make +1. So let's do -3 and +2. Okay, that would give us 4x minus 3x, which would give us positive 1x in the middle. Okay, and then in that denominator, same thing, let's factor. X squared breaks down to x and x. If it's going to multiply and make negative, one has to be positive and one has to be negative. Factors of 6 with a difference of 1, that's going to be -3 and +2. So we get -3x plus 2x gives us -x there in the middle. Okay. The first thing I notice is that we have the same factor in the denominator that we have in the numerator, which means we have a hole in the graph, and the hole is going to be the x value that would make that factor 0 in the denominator. So that's going to be -2 will be the x coordinate of that hole. To get the y coordinate of that hole, we're going to do y equals, and we're just going to substitute -2 in for x in the remaining equation, because from here on out, we're using the equation 2x minus 3 over x minus 3. Because these two graphs will look the same with the exception of this hole that's going to be in our graph. So we'll find the location of the hole and then plot it. So that's going to be y equals 2 times -2 minus 3. So negative. Okay, and then -2 minus 3. So -4 minus 3 is -7. -2 minus 3 is -5. Negative over negative cancels, and we get positive 7/5. Okay, so -2 and then +7/5. So 5/5 and 2 more fifths, and we're going to put a hole in the graph there. We're going to put a hole in the graph there. Okay, so now we want to decide if we have where our vertical asymptotes occur. And so I can see my function that I'm using now for the rest of the time. When would that denominator equal 0? And that would be at x equals +3. So I have a vertical asymptote at x equals +3. So I'm going to go ahead and sketch that in. And I'm going to redraw that hole so that that's clear that that's open. Okay, it's a little big, but no problem. Okay, so now the question is, do we have a horizontal asymptote or an oblique asymptote or neither? Now I want to compare the degree of the numerator and the degree of the denominator. They're both degree 1, so the degree is a tie, so the fraction in front equals y. So that's going to be a horizontal asymptote at y equals 2/1, which is just y equals 2. So I'm going to go ahead and draw in that horizontal asymptote at y equals 2. Okay, so if we have a horizontal, then that means that we don't have an oblique or vice versa. We can have at most one horizontal or oblique, but only one. Okay, so if we want to find our x-intercepts, we know x-intercepts have a value for x and a 0 for y. So if I put 0 in for y, that 0 equals that fraction. Now, when does a fraction equal 0? A fraction equals 0 when the numerator equals 0, so that's our shortcut there. We can just set the numerator equal to 0. But if you forget that, you can set the whole fraction equal to 0, and your first step will be to get rid of your denominators, which of course will get you back to where we started with the 0 equaling 2x minus 3. Okay, so we'll go ahead and add 3 to both sides, divide both sides by 2, and we get x equals 3/2. So we have an x-intercept at 3/2, comma 0. So 1.5 or 3/2. We do, in fact, touch the x-axis, so that's the closed point there. Y-intercepts, so y-intercepts will have a value for y and 0 for x. So let's go plug in 0 for x and see what we get there. That's going to be y equals, and again, we're using our simplified form of the equation. So 2 times 0 is 0, minus 3 is -3, over 0 minus 3 is -3, which simplifies, negatives cancel, 3 over 3 is 1. So that's going to be at 0, 1. So at 0, 1. And you can see our curve coming together here. We know that our graph is going to approach the vertical asymptote because we can never cross it, so it has to approach it. And then we know that this horizontal asymptote limits its end behavior. So as we go to -infinity, it's going to be approaching that horizontal asymptote. So that's the first piece of our graph. All right, now ask for other points. We need to see what the rest of the graph looks like. So what happens on the other side of that asymptote? So let's pick some numbers that are going to be easy to plug in. How about let's try 4 and 5 and see what our graph looks like. Okay, so if I plug 4 in for x, that's going to be 2 times 4 is 8, minus 3 is 5, over 4 minus 3 is 1, so 5 over 1 is just 5. Okay, so that's going to be the point 4, 1, 2, 3, 4, 5, so the point 45. Okay, if we plug in 5, 2 times 5 is 10, minus 3 is 7, over 5 minus 3 is 2, so that's 7/2, so that's 3.5. So at 5, we're at 1, 2, 3.5. Okay, and really 2 points is enough there for me to see what's happening. This is, remember, it's going to be approaching the asymptote, so it's going to be coming from that asymptote, and then in the long run, it's going to be limited by that horizontal asymptote there. And so that's enough for me to get that sketch of the graph. Now you can do the other points in a t-chart if you want, or you can just plug them in and find them yourself. Whatever you want to do there works. Okay, and behavior of this graph, we just want to write those statements to practice that. As x approaches infinity at the right end of the graph, y approaches 2, And if we want to be more specific, we can say it approaches 2 from above. The little plus sign in the exponent's position means it's approaching 2 from above. As x approaches negative infinity, y is approaching that horizontal asymptote at 2, but this time it's approaching from below. So we'll put a negative in the exponent's position, and that means that it's approaching from below. All right, let's try another one of these. Okay, so let's get this in factored form, see if we have any holes that cancel away or any vertical asymptotes, which, let's see. So that numerator is the sum of perfect cubes. So I'm going to factor that. I know it's going to be the sum of perfect cubes, so it'll be same sign, opposite sign, always positive. It's the cube root of the first term, which is x, the cube root of the second term, which is 1. We're going to square that first term, which is x squared, multiply them together, so that's 1x. And then we're going to square the last term, which is 1. Okay. In the denominator, I'm going to factor out my common factor. Both terms have an x, so I'll factor that out. That leaves me an x in the first term and a plus 1 in the second term. Okay, and right away, I see we're going to have a hole in this graph as well because x plus 1 over x plus 1 cancels. So we do have a hole. The x-coordinate of the hole is the value that would make that factor of the denominator 0. So that's going to be at -1. Okay. To get the y-coordinate, we're plugging into our new function, the x squared minus x plus 1 over x, which is the function we're using from here on out. So if I plug -1 in there, that's -1 squared is 1 minus a -1, so that's plus 1 is 2, plus 1 is 3, over -1 would be -3. So at -1, -3, just plugging in -1 for x in that remaining equation. So let's graph that. At -1, -1, 2, 3, I have a hole in the graph. So I'm going to do a big hole in the graph. Okay, the vertical asymptotes are wherever our denominator is 0 now that we have the equation simplified. So that's only going to be a vertical asymptote at x equals 0. Okay, so at x equals 0, I'm going to go ahead and draw in my vertical asymptote. Okay, now to decide if we have a horizontal oblique asymptote or neither. If we take a look at our simplified equation, the degree of the numerator is bigger by 1 than the degree of the denominator. If the numerator is bigger by 1, oblique, long division, and you're done. That means we have no horizontal asymptote. We're going to have an oblique asymptote, and we have to do long division to find it. So I'm going to do x squared minus x plus 1. So minus x. Just erase that. Minus x plus 1. And we're going to divide it by our denominator, which is x. So how many times does x go into x squared? It goes in x times. That's going to give me x squared. Subtract that from the line above. That cancels. Bring down your next term, negative x. How many times does x go into negative x? That'd be -1 time. -1 times x is negative x. When I subtract that from the line above, change the sign. So that cancels, and I bring down my next term. Now, I'm not even interested in how many times x goes into 1 at this point, because that's going to be my remainder, and we don't care about the remainder. You can go ahead and write it here if you want. It's going to be plus 1 over x, but we're going to disregard the remainder. Our oblique asymptote happens at the quotient without the remainder. So it's just this quotient, the answer we get without the remainder. So we have an oblique asymptote at y equals x minus 1. Okay, so there's my oblique asymptote, so let's graph that. That would have a y-intercept at -1, and it's an asymptote, so I'm going to put it as a dashed line, and its slope is +1, so up 1 and forward 1, up 1 and forward 1, so that's going to be that, and then down 1 and backwards 1, down 1 and backwards 1. Okay, so that would be our line there for our oblique asymptote at y equals x minus 1. Okay, what about x-intercepts and y-intercepts? Okay, well, first of all, on this graph, I know that my function can't cross the vertical asymptote, and it's going to be approaching this oblique asymptote. So my question is, where is it? Is it in this piece? Is it in this piece? Where exactly is it? I can tell my hole is here, so the rest of the graph is probably here. So let's just plug in some other values at this point to see where it's at. I know that there's no y-intercept because we have a vertical asymptote on the y-axis, so I know there's none there. But let's plug in some other values and see where we're at. So let's plug in like -2. Okay, so I plugged in -2 and -1/2. My work's right here above. I actually got -7/2 for both. For both, I got -7/2. And so that means at -2, we're at -3.5. And at -1/2, we're at -3.5. There's -7/2. Okay. All right. So what's going on there? Well, we know that we're approaching that oblique asymptote in the long run, and we know that we're approaching our vertical asymptote. We're approaching that vertical asymptote. Going on the other side of that hole, going through that point, approaching that vertical asymptote. Okay, so let's get some graphs, some points on the other side of that vertical asymptote. So let's try 1 and 2 maybe. So if I plug in 1, I'm going to get 1 squared is 1, minus 1 is 0, plus 1 is 1 over 1. So 1 is going to be 1. So at 1, 1, it's right there. Okay, and then let's plug in 2. So 2 squared is 4, minus 2 is 2, plus 1 is 3 over 2. So that's 3/2. So at 2, we're at 1.5. Or 3/2. Okay, so it's definitely coming in, approaching this oblique asymptote here already really quickly, and I know it's got to approach my vertical asymptote in the other direction. So make that look like it's approaching that a little bit more smoothly. Okay, approaching that vertical asymptote as well. Okay, and so there's a nice little sketch of our graph, just the hole and those two pieces. Let's make our end behavior statements. As x approaches infinity, y is approaching the line x minus 1 from above, and as x approaches negative infinity, y is approaching the asymptote at x minus 1 from below. Okay, let's try one more of these. So we need to get that denominator factored and see what we have. Got x plus 1 over x and x, plus and minus. So it'll be -3 and +2. Okay, so we don't actually have any holes this time. None of our factors cancel, so we'll have no holes in the graph, so that's kind of nice. Now, we have vertical asymptotes at whatever would make that denominator 0. So we have vertical asymptotes at x equals -2 and x equals +3. And you can put a semicolon between them. You don't have to put an and sign. You can just list them like that. Okay, so let's graph those. At x equals -2, we've got a vertical asymptote. At x equals +3, got a vertical asymptote. Do we have a horizontal or oblique asymptote? So how does the degree of the numerator compare to the degree of the denominator? Nothing canceled here, so you can look at that original equation. There it's easier to see the degree is bigger below. Bigger below means horizontal asymptote at a y equals 0. So that means we won't have an oblique asymptote because you can only have at most one horizontal or oblique. So we have a horizontal asymptote at y equals 0. Go ahead and graph that. Okay, and now let's go ahead and find our x-intercept. Of course, we'll have a value for x and a 0 for y. So I'm going to set that fraction equal to 0. A fraction is equal to 0 when the numerator equals 0. So that would be when 0 equals x plus 1. So x equals -1. So that would be -1, 0 is our x-intercept, only 1. And so look at that. That's actually a crossing point. It fell on our horizontal asymptote. Horizontal asymptotes can be crossed. They absolutely can be crossed in the short run or in the middle of the graph, but they will limit the end behavior. At the end behavior, it'll approach the horizontal or oblique asymptote. Okay, y-intercept has a value for y and a 0 for x. So let's put a 0 in an x's position. So that's going to be y equals 0 plus 1 is 1 over 0 plus 2 is 2 times 0 minus 3 is negative 3. So 2 times negative 3 is negative 6. So y equals negative 1/6. Okay, so 0, negative 1/6, really close to it, really close to it. Okay, all right. And let's see. So let's go ahead and get some other points so we can finish off this graph. I see that as I move left to right here, that looks like it's coming down. I want to check just one more point in there just to be sure. So let's plug in 1. 1 plus 1 is 2 over 3. I'm going to plug into the original. 1 squared is 1, minus 1 is 0, minus 6. So that's 2 over negative 6, which gives me negative 1/3. Okay, so it's going to be negative 1/3. So still negative, but definitely coming down. Okay, so I can see that trend that's coming down. So I know that's coming down and it's going to be approaching that vertical asymptote. Let's see if I can do that a little smoother. It's coming down and it's going to be approaching that vertical asymptote, which means as we came from the left, it was coming from the up direction, approaching that vertical asymptote. Okay, so it's going to be coming down, crossing the x-axis at our crossing point, and then coming down and approaching our other vertical asymptote. All right, what about on either side of those vertical asymptotes? So let's go like negative 3 and see what's happening over there. So if we plug in negative 3 plus 1 is negative 2 over negative 3 squared is 9, plus 3 is 12, minus 6 is 6. So that's also going to be at negative 1/3. So at negative 3, we're at negative 1/3. Okay, and let's see what's happening at negative 4 there. Okay, so negative 4 plus 1 is negative 3 over negative 4 squared is 16, plus 4 is 20, minus 6 is 14. So negative 3/14, negative 3/14. Okay, so our question is it's obviously a little fraction. So that's going to be a little closer to that asymptote. So we're approaching that asymptote there. So we can go ahead and draw that in there, which means then we're going to be coming, and we see we're coming slightly down. So we are going to be coming down and approaching that vertical asymptote there. As we move left to right, we were coming from that asymptote, really close to it already, and then starting to come down. So we'll approach that vertical asymptote. All right, what about on the right side of that asymptote? So 1, 2, 3, 4. So let's try positive 4. So positive 4. 4 plus 1 is 5. 4 squared is 16. Minus 4 is 12. Minus 6 is 6. So 5/6. So at 4, we're at positive 5/6. Let's try 5. 5 plus 1 is 6. Over 5 squared is 25. Minus 5 is 20. Minus 6 is 14. So 6/14. So just under a half. So it is coming down just under a half. Okay, so we are coming down, approaching that horizontal asymptote. And where are we coming down from? We're coming down from this vertical asymptote because we know it has to approach it because it can't cross it. Okay, and so that's a rough sketch of that graph. And behavior as x approaches infinity, y is approaching 0 from above. As x approaches negative infinity, y is approaching 0 from below.